How do engineers design amplifier input impedance matching networks? Imagine trying to push a swing with just the right amount of so it moves smoothly without wobbling or stalling. That's similar to what engineers do when designing amplifier input impedance matching networks. They want to transfer the maximum signal power from the source, like an antenna or sensor, into the amplifier without losing any signal or causing reflections. To do this, they focus on matching the input impedance of the amplifier to the source impedance, which often is around 50 ohms in many systems. Impedance is a combination of resistance and reactance. Resistance is straightforward, like the friction you feel when pushing a box across the floor. Reactance, however, is due to inductors and capacitors and causes the impedance to change with frequency. For optimal power transfer, the input impedance of the amplifier must be the complex conjugate of the source impedance. This means if the source has an inductive reactance, the amplifier should have an equal but opposite capacitive reactance. When these are matched, signals flow smoothly and reflections are minimized. The first step is to measure or estimate the input impedance of the amplifier at the frequency you plan to operate. This involves testing or simulating the amplifier with tools like network analyzers to see what the impedance looks like. Once you know the impedance, the next step is choosing a matching network topology. The simplest is called an L network, which uses one inductor and one capacitor arranged in an L shape. These are easy to design and work well for narrow bandwidths. For broader frequency ranges, engineers often use pi or T networks, which include 3 reactive components to cover wider bands. At very high frequencies, transmission line transformers or stubs are used, especially in radio frequency applications. Calculating the component values involves converting the known impedances into normalized forms, usually relative to 50 ohms. Then, formulas based on reactance and susceptance help find the right inductor and capacitor sizes. Engineers often use the Smith chart, a graphical tool that visually shows how impedance transforms as signals pass through reactive components. This makes it easier to see how to adjust the network for perfect matching. After the initial calculations, engineers run simulations using software like LT-Spice or specialized RF design tools. These simulations help verify the performance and allow for fine-tuning of component values. Practical considerations also come into play, such as the parasitic resistances of real components, which can affect performance at high frequencies. The bandwidth of the matching network is another factor. Narrowband networks work well at a single frequency but may not perform outside that range. Wideband networks are more complex but necessary for applications needing signals over a broad spectrum. Power handling is also important. The network components must withstand the expected signal power without distortion or damage. The physical layout of the circuit, especially at radio frequencies, influences impedance matching. Proper placement of components on the printed circuit board reduces unwanted parasitic effects. In real-world applications, input impedance matching is vital in low-noise amplifiers, radio frequency power amplifiers, and other analog electronics. For example, in antenna systems, matching networks connect the antenna's typical 50 ohm output to the amplifier's input, ensuring efficient signal transfer. Overall, designing these networks involves understanding the source and load impedances, selecting the right topology, calculating precise component values, simulating the design, and considering practical factors to achieve the best possible performance.